So let's take an example of application of the residue theorem. Say we want to calculate this integral. X is a real number. Nevertheless, we will see that going into the complex plane and applying the residue theorem will give us a solution to this integral. Let's define a function f of a complex variable. This function has two poles, one in plus I and one in minus I. We define the closed contour gamma around one of the poles. It is the union of a contour from minus r to r on the real axis with a semicircle of radius r on the upper plane. We now calculate the residue for the pole which is inside the contour. We now apply the residue theorem. We then decompose the integral into the different intervals of the contour. The first part on the real axis is getting close to what I'm looking for. And of course it would be ideal if the second part was going to 0 for large radius. On the semicircle C, the complex number z can be expressed as r exponential I theta with r being a constant. So we can replace the integral over z into an integral over theta. So when we take r goes to infinity, this simply goes to 0. So we push the contour so that r goes to infinity, and this does not change the integral on the closed contour gamma because there is only one pole inside this contour. And of course 1 over 1 plus x squared is even in x. Therefore the integral from minus infinity to plus infinity is twice the integral from 0 to infinity. So we have solved our integral. It is just pi on 2.